You ever wonder how we measure something as tiny as an atom or as mind-bogglingly huge as a galaxy? It sounds almost impossible, right? Well, what if I told you there's a simple, super elegant system that makes it all work? Today, we're going to pull back the curtain on the hidden language of physics, the one we use to measure the entire universe. It's a huge question, isn't it? I mean, from the speed of light to the weight of a black hole, so much of physics is really just about measurement. And what's wild is that there's this common framework, a shared language that lets physicists make sense of it all. So what's the secret sauce? Okay, so it all starts with one core idea. If we want to understand the language of physics, we've got to start with its most basic component. Let's break down the anatomy of what a measurement is really made of. At the heart of everything is this idea of a physical quantity. And it's a way simpler idea than it sounds. Basically, if you can measure it and put a number on it, it's a physical quantity. The distance to your work, how long your favorite song is, how hot your coffee is, yep, those are all physical quantities. Now, this is the crucial part. Every single physical quantity has two parts, and you need both. First, you've got a number, which tells you how much, and second, you have a unit, which tells you of what. You can't have one without the other. They're a package deal. Let's really hammer this home. If I just walk up to you and say 5, what does that even mean? 5 what? 5 apples? 5 hours? It's totally meaningless, right? But the second I add that unit and say 5 meters, bam! Now you have a concrete, real measurement you can actually use. The unit is what gives the number all its power. And you see this structure everywhere. Take mass, for example. 2 kilograms. 2 is the value, kilograms is the unit. It's that simple, powerful combination that gives us a precise measurement. Or here's another one we use all the time, time. 10 seconds. You've got the number, 10, and the unit, seconds. Together they form a measurement that everyone on the planet understands instantly. And let's do one more for temperature. 37 degrees Celsius. Again, same pattern, the value, 37, and the unit, degrees Celsius, working together. This simple two-part structure is the fundamental grammar for every single measurement in science. So, we've got the basics down, but here's where it gets really cool. It turns out that not all quantities are created equal. Some are the actual pillars that all other measurements are built on top of. A really great way to think about these is like the primary colors of physics. You know how you can take red, yellow, and blue and mix them together to create a whole rainbow of other colors? Well, physicists do the exact same thing, but with a small set of basic quantities to describe pretty much anything in the universe. These are what we call fundamental quantities. And the keyword here is independent. You can't break them down any further. You can't make them by mixing other quantities together. They are the absolute bedrock, the starting point for everything. This idea is so huge that our entire global system of measurement, you might know it as the SI system, is built on just 7 of these fundamental quantities. 7, that's it. So, you want to know what the magnificent 7 are? All right, here they are, the alphabet of the universe. You've got length, which tells us about space, mass, which tells us about matter, and time, which is all about change. Then we've got electric current for the flow of charge, temperature, which measures heat energy, the amount of a substance, which is super important for chemistry, and finally, luminous intensity, which is all about the brightness of light. That's the whole list. These 7 are the only letters physicists need to write the entire story of the cosmos. Okay, so we have our alphabet, our 7 fundamental quantities. Now for the really fun part. Let's start using them to build things. If these are the letters, how do we start forming words and sentences to describe the incredibly complex world all around us? This is where derived quantities come into play. And the name says it all, right? These are the measurements we derive by combining our 7 fundamental building blocks in all sorts of clever ways. This is how we level up from the basics to the complex stuff. So, to stick with our analogy, if the fundamentals are our ABCs, then derived quantities are the words we build with them. Words like speed, volume, and force. This is how we go from simple measurements to describing the awesome phenomena of the universe. And this table is basically the recipe book. Take a look at speed. What is it really? Well, its recipe is just length divided by time. That gives you the unit meters per second. What about volume? Easy. It's length times length times length, or meters cubed. Even something that sounds really complex, like force, is just a recipe of mass times acceleration, which, by the way, is also derived from length and time.
It all connects back. It's so elegant.
This quote just nails it. The whole system is incredibly efficient. We don't need a million different independent measurements for a million different things. All we need is this handful of basics and the rules for combining them, and suddenly we can describe the whole shebang. So the big takeaway here is this. Our universe, with all its infinite complexity and mind-blowing phenomena, can be measured and described using a system that comes down to just 7 fundamental rules. It's a powerful reminder that there's a beautiful simplicity and order hiding underneath it all. And that leads us to one last really fascinating question to think about. This system of 7 has served us incredibly well. But as we keep pushing the frontiers of science, as we start exploring mysteries like dark energy and quantum gravity, you have to wonder, will our 7 fundamentals be enough? What new, undiscovered quantities might be waiting out there, ready to unlock the secrets of the universe of tomorrow?